Welcome back to ECE 320A. This is Unit 9, which means we're talking about transfer functions and how they behave relative to particular signals or input waveforms, what kind of output waveforms they produce. In this particular video, I want to illustrate what I want you to understand, special condition where you can actually apply a bounded input waveform to a system that has poles not in the right half plane, but right on the imaginary axis. With the correct or the right input waveform, you can actually produce or generate an unbounded output response. And that's what we want to look at or examine in this particular video. So let's look then at bounded inputs that can produce unbounded outputs. That's with marginally stable systems. And by that, I'm using the description that a lot of people have used. Marginally stable system, I'm going to say poles on j omega axis. So here's our review. First, hopefully this is very straightforward. Suppose that I wanted to look at the inverse Laplace transform of 1 over s. Then in the frequency domain, that looks like a single pole right at the origin. That's what the S-plane picture shows. And the time domain, if we inverse Laplace transform that 1 over s transform, we produce 1. So in the time domain, we have a waveform that looks like that. Suppose we now look at 1 over s squared, and now those two x's are really right on top of each other, but I'm trying to emphasize the fact that I have two poles at the origin. That now produces a growing waveform as a function of time. If we were to sketch that waveform, we now have this particular response as a function of time. So these are just transform pairs that we should be very comfortable with. What if and now what you can think of is if you now had 1 over s and you knew that that produced a 1, now you look at 1 over s squared, you've now repeated that pole factor at the same location. And when you repeat a pole factor, what is sort of our mantra? It's put a t in front of it. So in this case, we really could think of this as 1, and then we have a t in front of it or behind it, but we now end up with just a growing function with respect to time. What if we now look at 1 over s cubed? Now we've put another s on top, so now we have 3 poles. Again, I've staggered those in location just for graphical reasons. But now we're sticking another t in front of our t. Now, obviously, we have to adjust a little bit with the coefficients, but we stick another t in front of it, and we now have t squared, so that we now have a waveform as a function of time that's actually growing even faster than what we had before. We could keep going, and the pattern then says that if we start with 1 over s, and now we have n plus 1 poles at the origin, then that's going to produce in the time domain a polynomial t to the nth power. That's really growing as a function of time. And we really are just continuing to put a t in front of it for every pole we stack on top of the original poles at the origin. Now if we have n plus 1 poles at the origin, we have t to the n in terms of a time response behavior. Let's look at that then in terms of input waveform and system characteristics. What happens if we integrate a constant? In the time domain, here's our time domain block diagram. We have an input that's just a constant. Let's say it's A, and our system now is a pure integrator. Whatever comes in, we simply integrate it. What's y of t? And this you should actually remember from calculus. What happens when we integrate A? Well, now we obtain AT. And that's growing with time. And you can think of that as now you have a constant input signal and what are you doing with an integrator? Well, you're just adding up the area underneath that integral or that constant. Here is our constant, and as we continue to add or integrate area, then we simply get AT at the output. That should be somewhat intuitive from our calculus. If we look at that in the S domain, what does that translate into? We simply Laplace transform A, the constant, and we get capital X of S, which is A over S. An integration operation in the time domain becomes a 1 over S operator in the frequency domain or in the S domain, and we know how to compute the output based on the input. To produce the output, we simply multiply the system's transfer function, which in this case is 1 over S, times the Laplace transform of our input, which is A over S. We now have for the output transform expression, capital Y of S, that's now A over S squared. But remember our review. What did we do, or what was happening when we had a 1 over S squared? Now we actually put a t in front of it, or we now actually go from this to AT, and this is now going back into the time domain, where we now are inverse Laplace transforming A over S squared. Now we have AT, so our understanding is consistent. We put in a bounded input, we integrate it, and what does that look like in the frequency domain? Well, that integrator is an operator that has a pole at what location? What value of S causes that denominator to vanish? Well, that one is pretty easy. S equal to 0 causes the denominator to vanish. We now have a pole sitting at 0 at the origin. That's right on the imaginary axis. Now, if we place a signal that also has a pole at that location, that now produces a repeated pole at the imaginary axis or right at DC or right at the origin, and that now leads to unbounded behavior in the time domain. So what we're seeing then is that we can take a bounded input signal, a constant, and that can imply that we can produce an unbounded output signal. Now, if that's the case, our system was needing to have poles where? Well, this particular case needed that pole to be right on top of where the pole was located for the signal, and in that case it was at the origin. Here we can actually generalize that and say that we really only need poles on the imaginary axis if we locate or have a bounded signal that generates poles at exactly those same locations on the imaginary axis. So we need a system with poles on the imaginary axis or on the j omega axis. And that's going to produce an unbounded signal. That takes now a specific input. If we put in a sinusoid and we integrated it, we're going to get a sinusoid out. It's not going to go unbounded. So let's look at that. Suppose now we apply a sinusoid, cosine omega naught t, to a system that has a transfer function 1 over s squared plus omega naught squared. And you might start having the hair on the back of your neck stand up, because now you should be able to see that, oh, we have a frequency at the input of omega naught, and our system actually has poles at, and now let's answer these questions. what does capital X of S look like in the frequency domain? If we Laplace transform cosine omega naught t, we end up with S over S squared plus omega naught squared. And where are the poles of capital H of S? Those are the values of S that cause the denominator to vanish. And those are poles then at plus and minus j omega naught. And that's exactly where the poles of our signal are located. And we can now look at or examine the output. Y of S is the product of H of S, which is 1 over S squared plus omega naught squared, times capital X of S, which is S over S squared plus omega naught squared. Or we now have this capital Y of S is S over S squared plus omega naught squared squared. And what do we know happens when we have a T or we have a repeated pole? That's when we can say this mantra that is, put a T in front of it. So now Y of T actually becomes T, and if we don't worry about what the exact numerator is, we know that we have some kind of combination of cosine at the input frequencies value, omega naught t, plus a sine wave. But because of this repeated pole, that says put a t in front of it. Or you could say that we have t, let's say bar cosine omega naught t plus theta, because we know a combination of cosine and sine is really a single cosine or a single sine with a phase shift. Our conclusion then from this discussion is that with the right or with the correct bounded input signal, and that input signal has to be at the same frequency as the poles of our transfer function, and those are located on the imaginary axis. With the right bounded input signal and a system that has poles on the j omega axis, an unbounded output signal can be created. Let's look at an example, a numerical example. We've already looked at this in general, but suppose that now somebody gives you a system and they say, okay, your system is 6 over s squared plus 1. Probably the very first thing that you want to be doing when somebody gives you a system is figuring out what does it naturally like to do. And what it naturally likes to do is vibrate or behave consistent with where its poles are located. In this case, we have poles at locations where s squared plus 1 equals 0. This is a quadratic. We expect to have two poles. S squared is equal to minus 1. So in fact, we have s equaling plus and minus j. We actually have poles on the imaginary axis. We now have, for our system, poles at plus and minus j. Boom. Now, what do we know? We now know, based on our conclusion from before, that we can produce a bounded input that will actually cause that bounded input being passed through this particular system to actually generate or produce an unbounded output. And what is the input? What's the structure of our input? And let's just talk about it in the frequency domain. That's really where we want it to be located. And I'm going to color code this. Whoops. Suppose that I now say my input is red. And I want this to actually correspond to a bounded time domain waveform. But I want that bounded input waveform to be such that when it's applied to this system, capital H of S, that has poles at plus and minus J, that it will produce an output that goes unbounded with time. What does X of S, capital X of S, need to do? Well, it actually needs to have poles that are right on top of those poles that are on the imaginary axis. And we can do that with that particular capital X of S. So if we did this, this is now a bounded input. In fact, what is little x of t? Little x of t is in fact sine of omega naught. Omega naught is 1. X of t in the time domain is sine of t. And what is our output? Now our output, y of s, the Laplace transform of the output, is 6 over s squared plus 1. There's our transfer function times capital X of s. Well, that's just going to put another s squared plus 1 factor in the denominator. And what does this guy look like? This now is going to be what is it going to be? Let's just now say that it's some multiple. Let's not worry about the multiplier or the constant. But because of this repeated pole, we put a t in front of it. So that's going to generate a t and this s squared plus 1, and we don't have an s in the numerator in this case. So now we simply have a sine at the frequency omega naught equal to 1. So here is our omega naught in the numerator. And now what does this y of t do? Putting a t in front of it now causes this sinusoid to grow. Its envelope is now growing as a function of time. So this now produces an unbounded output by applying a bounded input. Sine of t is bounded, but we started with a special transfer function. That transfer function had poles on the imaginary axis. The combination of that with a signal that has poles right on top of the transfer function poles on the imaginary axis produces a repeated pole, and that repeated pole says put a t in front of it, and now we have an unbounded output for a bounded input.